Yeah, we can go
Hi
ahead.
everyone, I'm Shi Tam. I'm a postdoc working in Asia A in Taiwan. First of all, I would like to thank the organizer to give me this chance to talk about our work here. So today I will talk about this likelihood free-form modeling for cluster rebalancing and cosmology. In this study, we use galaxy cluster as a target to constrain these cosmological parameters. Galaxy cluster, they are the largest gravitational bound object in our universe. They are very massive and dominated by the dark matter. Their structure formation history is very sensitive to the initial density fluctuation in the early universe. So galaxy cluster, they are usually act as a sensitive pool for this background cosmology. There are some key observable for this cluster cosmology study, like the cluster abundance, which is the number count of galaxy cluster in a certain sky survey. And also their mass is important, so we can calibrate this cluster mass from the rebalancing analysis. Once we have this observable, we can build up a model to do the inference to infer the cosmological parameters, omega m and sigma a. Traditionally, when people do this cosmological inference, they will use the Bayesian approach, which is based on the Bayes theorem. So we can compute the posterior distribution based on this likelihood function and also prior. In this Bayesian approach, it requires us to know the likelihood function, and usually the Gaussian likelihood is assumed. However, this galaxy cluster, they are highly nonlinear objects in our universe. So there could be some non-Gaussian contribution that dominate the noise due to this nonlinear physical process and instrumentational effect. And this will cause the bias in this final posterior constraint. So recently, the likelihood free-form modeling provides an alternative approach to do this cosmological inference. For the likelihood-free inference, there are several different methods like the ABC or DELFI. And in this study, I will focus on using DELFI for our cluster cosmology study. For this likelihood-free inference, we first need to develop a forward model to simulate the observable. So in our study, we develop our own end-to-end forward model. We start from inputting some initial parameters of the cosmology, omega m and sigma a, into our forward model, and then it will simulate the cluster observable, like the cluster abundance and also the cluster rebalancing analysis data. The main goal of this end-to-end forward model is to provide us a more flexible and complex cluster modeling method. It should include some complex physical process and also the selection bias and also the instrumentational effect. This shows you more details procedure about how we develop our own forward model. So starting from some cosmology, we sample the galaxy cluster from the halo mass function, and then we use the cluster halo model to represent this massive object. More importantly, we need to implement this survey selection function. So different telescope, like optical telescope or X-ray satellite, they have their own survey selection function. So we need to decide what kind of cluster survey we are simulating. And in this analysis, we assume that our galaxy cluster are X-ray detected. So we implement the eROSITA-like survey selection function in our simulation. And then we are able to create a X-ray detected galaxy cluster sample. And then we can calculate some properties of this object, like the weak-lensing shear signal or the X-ray properties. And finally, this forward model will output a summary statistic for us. In our case, it's the simulate number count of galaxy cluster and also the stack weak-lensing profile. And then we can compare this output from the forward model with the observational measurement, and then to constrain this omega m and sigma a. In our forward model, we implement the noise, for example, the weak-lensing shape noise, and also the possible measurement uncertainty in our simulation, so that the final output from this forward model will already contain the noise, so that we don't need to compute the covariance matrix for our simulation or for our analysis. So once we develop this forward simulator or forward model, we can then generate a large sample of simulated data. And then we can input this simulated data together with the observed data set into this neural density estimator to compute the likelihood and also construct the posterior distribution. In this study, we used the package PyDelFi to do this simulation-based inference. Here, I show you the result with this cosmological forward simulator. So we create a mock observed data using the flat lambda CDM cosmology with omega m equal to 0.28 and also sigma a equal to 0.82. And we assume that our galaxy cluster, they are X-ray detected. So we use the eROSITA light selection function in our simulation. And we have the cluster survey that are covering a total sky area of 50 degrees square. In the right-hand side here, I show you the posteriors obtained from our PyDelFi. So in total, we have 3 parameters, omega m, sigma a, and a. A here set the mass scale for our cluster survey. And we consider 2 different noise levels in our simulation. The first one is the ideal case, noise-free case with a large number of background galaxies, 400 galaxies per arc-minute square. And the second case, the orange one, is much more similar as to a ground-based observation with 20 galaxies per arc-minute square. And here, the black dashed line is the fiducial value we use to generate this observed data set. So you can see that the posteriors obtained from this PyDelFi is consistent with this fiducial value. And with a larger noise level, we will have a broader distribution for these posteriors. And also you can see that, you may also see that this peak of these posteriors is slightly offset from the fiducial value. This is because we only use one realization from the simulation as an input. And this realization already contains the noise. And this is similar as the case of the real observation or real experiment in daily life. If they already contain the noise in this experiment, then the posteriors will not perfectly align with this fiducial value. If we have 100 observation or experiment, then we can measure the average of posteriors distribution. Then this average posterior should center on this fiducial value. But in our case, we only use one measurement or one realization as an input. So you can see that it's slightly offset from this fiducial value, but this makes sense. So we found that this simulation-based inference can well constrain these cosmological parameters without bias. And we also compare this result with the ABC PMC. So in the left-hand side here is the posteriors obtained from ABC PMC. We use the same forward model and also the same realization as an input. So you can see that the posteriors obtained from these 2 different likelihood-free inference, they are consistent with each other, while ABC have a wider posteriors distribution and more noisier. And also ABC is much more computationally expensive, and it will suffer from the problem of this vanishingly small acceptance rate. PyDelFi gives us a much more efficient method to conduct this kind of study. So these are the results that we published last year in Time Adele 2022 to demonstrate this SBI approach is feasible for the cluster cosmology study. And recently, we have started another project by applying this likelihood-free forward modeling framework on the real data set. We want to do the weak lensing mask calibration for the galaxy cluster in XXL survey using the blind HSC weak lensing catalog. So we will use this likelihood-free approach for this weak lensing mask calibration. The main goal is to constrain the X-ray observable cluster mass scaling relation. In order to achieve this goal, we need to implement more realistic features and also noise in our forward model. So these are the items that we recently add in our simulator. Like we now have a much more realistic XXL survey selection function as a function of X-ray count rate and quant radius. Now we are able to model this X-ray observable, X-ray temperature, and X-ray luminosity. And also for the weak lensing part, we consider the more realistic redshift distribution for the source background galaxy. And also we consider the weak lensing mass bias that is caused by the triaxial shape of the dark matter halo and also the substructure in the larger scale. Another important thing that we need to do is to find an optimal summary statistic for this study. We have tried different data vector and combination of cluster properties. So far, we found these three different items are very useful and sufficient for this weak lensing mass calibration. So the first one is the cluster number count as a function of redshift. And also we need to have the stack weak lensing profile for different temperature beams to calibrate this weak lensing mass. And then we also need to have X-ray temperature and luminosity to link with the true halo mass. So here I will show you the result, preliminary results using this upgrade forward model with the mock observed data set. You can see now we have 8 parameters, omega m, sigma a, and additional 6 parameters to describe this temperature mass scaling relation and luminosity temperature scaling relation. The posteriors are constrained from this pi-DELFI, the SBI approach. You can see that it's very consistent with this fiducial value. So now we are applying this method and also the upgraded forward model on the blind HRC weak lensing data and also the XXL galaxy cluster catalog. So in conclusion and future work, if we want to have an accurate SBI, it will require us to have a realistic forward model. And once we have this realistic forward model, this SBI will provide us an unbiased approach to infer the posteriors. And we found that the DELFI is much more efficient than the ABC. Now we are applying our upgrade forward model with SBI on the real HRC data to calibrate the galaxy cluster mass, which will be very useful for the future cosmological study. And we'll stop here, and I'm happy to take any questions. Thank you.
Great, thanks so much. The speaker is online, correct? To take questions. Is the speaker online?
Yes, I'm online.
Okay, great, thanks. Thanks so much. Okay, so are there questions here in New York? Yeah, go ahead, Adrian.
Hi, thanks for the nice talk. Just a general question, maybe. What is the most difficult thing you're finding when applying to the real data?
Yeah, so because we are now developing our model, so in our first paper, we have some simplified assumption. So there are some limitations, so the noise are underestimated. But now we are developing an upgrade for model, trying to put more realistic noise so that it can match with the real data set. For example, for the weak lensing analysis, there maybe have any miscentering problem, and we are now trying to implement this into our forward model as well. So for example, the weak lensing mass bias due to the triaxial halo shape, that this will also cause some scatter in the weak lensing profile. So now we are dealing with this kind of issue. Thank you.
Are there questions in Paris?
I think that everybody is digesting at the moment.
I understand.
I don't see any hand raised at the moment.
No problem, and no questions on Slack. Okay, if not, let's thank our speaker again, especially for staying up late, I think.
Thank you.